Okay, in this section we're going to talk about properties of logarithms. Now we're just going to talk about the properties and kind of see where they come from and how they work. We're not going to see why we use them or how we use them until the next section in 6.6. So for right now we're just working with these properties, and the why we would do this might not make sense yet, but let's just work with how it actually works. All right, so the first one looks like this. A to the log base A of m. Okay, A to the log base A of m, and this is going to be equal to m. Okay, so what this says is that if we have a log inside of an exponential, so we have a log inside of an exponential, the bases match. So remember, they should be inverses. And so the composition should cancel out and we should be left with m. So this, we looked at the other one in the previous section. This is the other half of the of proving that they're inverses. So we did an exponential inside a log. This is a log inside of an exponential. Okay, so why does this work? All right, I'm not gonna test you on this, but let's see why it works. So let's say we have a to the log base A of m, and we want to know what that's equal to. So we're just going to say that that's equal to y because we don't know yet. All right, so when we convert this to this is exponential. When we convert this to logarithmic, okay, ignore this stuff in here. This is just an exponent. So we've got a to the something is equal to y. So when we convert this to a logarithm, the base is a, and the exponent is this thing. So we're going to have log base a of y is equal to the exponent log base a of m. Okay, so I'm converting this to log form. The base is a, so log base a of y is equal to the exponent log base a of m. So we end up with this. Okay, so we looked at the graphs of exponential and log in the videos and in class, and we saw that both log and exponential are 1-to-1. And so what that means is that if you have two logarithms that are the same, then what's on the inside has to be the same. So y has to be equal to m because logarithms are 1-to-1. All right, so what that means is that a to the log base a of m, this is actually equal to m. So a log inside of an exponential cancels out just like we want to. So this is the other direction that shows us that these are inverses. All right, so let's look at a couple examples of how this actually works. So let's say we have 2 to the log base 2 of 5. 2 to the log base 2 of 5. So you see the base is 2, the base is 2, so they match. So that means that they're going to cancel out, and we're going to be left with just 5. Okay, if we have 3 to the log base 3 of x plus 2. We see the base is 3, the base is 3. That means these are going to cancel out, and we're going to be left with x plus 2. Okay, now the way that we really come across these the most is with e and natural log. Remember, e and natural log are inverses. So let's say we have e to the ln of 3x minus 1. All right, now remember, you don't see the bases for these, but remember e and ln go together. Ln is actually log base e, so even though you don't see it there, you've got to remember that it is. So e and natural log cancel out, and you're left with 3x minus 1. Okay, so a log inside of an exponential, those are inverses, they'll cancel out, and you're left with just the exponent. Okay, second property is the one that we already looked at. So this is log base a of a to the r. They use r in this section instead of b. We already looked at this in the last section. We know that these are also going to cancel out and give us r. So if we have an exponential inside of a log and the bases match, they're going to cancel out. So this is where we were looking at things like log base 3 of 81. And we say, okay, can we write these with matching bases? Yes, we can. 81 is the same as 3 to the 4th. The bases match, so they cancel out, and we're left with the exponent 4. All right, so we already looked at that one a little bit. Okay, the next few properties come from exponent rules. Okay, so they look a little bit weird at first, but if you remember they come from exponent rules, that'll help a lot. So the third property is that log base A of m times n is equal to log base A of m plus log base A of n. Okay, and this looks a little bit weird because there's not really anywhere else in math where we can go from multiplication to addition like this. So why does this work? Okay, so on page 452 in my book, they have the full explanation. We're gonna kind of go through a modified version of it, but if you want to see the full explanation, it's 452. Okay, so let's say that we have log base A of mn. Okay, so we're starting with this left-hand side, and we want to rewrite this. So we know what to do if, sorry about that, that came out blobby. Let me rewrite that. All right, we know what to do if the bases match, but we can't really do anything with this. Well, we know from our exponential section that we can rewrite any number we want with any base we want because we saw the graph of it. Okay, we usually deal with whole numbers, but we can rewrite m with base A with some exponent s. We just don't know what it is. And we can rewrite n with some base A with some different exponent t. Okay, so we know that we can do that. And so that means that we can rewrite this base A. We would have a to the s times a to the t. Now this is where our exponent rules that we already know kick in. What do I do here? If I have a to the s times a to the t, we're going to add the exponents. So we're going to have log base A of a to the s plus t. So log base A of a to the s plus t. Now rule number 2 kicks in. The bases match. So our log and our exponential are going to cancel out. The bases match and we're left with s plus t. All right, but what is s and what is t? Well, we've got to come back up here. We want to know what s is. If we want to know what s is, we need to change this to log form. So the base is a, the exponent is s, so we've got log base a of m is equal to s. And doing the same thing over here, we've got log base a of n is equal to t. Okay, so converting this to logarithm, we get that s is the same as log base a of m, and t is the same as log base a of n. Okay, so we get this property by looking at exponential rules. So this is where we get the multiplication going to addition. That's actually a rule that you already knew. We're just looking at it in a different form with logarithms. Remember, logarithms are exponents, so the rules are tied into exponential rules. Okay, so now let's see how to actually use this. Now that we see that it works. All right, so let's say that we have log base A of, let's say we have 5x. Log base A of 5x. Okay, so we know that this is log base A of 5 times x, so that means that we can break it up as log base A of 5 plus log base A of x. So a product becomes a sum. All right, let's say we have log base 2 of xy. Log base 2 of xy. So you say, okay, that's x times y. Multiplication becomes a sum. So we can make this log base 2 of x plus log base 2 of y. Okay, so product becomes a sum. Now, the cool thing is that we can do this multiple times because for however many products we have, we can break it into sums. So let's say we have like log base 3 of a times b times c. Okay, I know that I can break up the a and the b, and then I know that I can break up the a and the bc, and then I know that I can break up the bc, so I can actually just break these all up in one step. So I'd get log base 3 of a plus log base 3 of b plus log base 3 of c. Okay, so I can actually break all of those up in one step. If you don't break them up in one step, then you would do it in 2 steps and you'd get the same answer. Okay, so that's how our third property works. It also works for, let's say we have natural log. So we have natural log of 6y. Okay, natural logs work the same way, it's just log base e. So we say, okay, this is 6 times y, so we can make this natural log of 6 plus natural log of y. Okay, so moving on to property 4. Property 4 says if we have a fraction, so log of m over n, so we've got a fraction inside, that is going to break up as log a of m minus log a of n. Okay, so again, this comes from exponent rules. We won't go through the whole thing, but if you imagine that what we just did in the last rule comes down to this exponent rule, and what do we do when we have exponents in a fraction? We subtract them. Okay, so before we had multiplication, we added them, but in a fraction, you subtract them. So that's where this minus comes from, log of m minus log of n. Okay, so looking at this one, let's say we have log base 3 of x over y. We're going to get log base 3 of x minus log base 3 of y. Okay, so when you're doing these, notice that when you break them up, each one is going to get a logarithm, and all of the logarithms are going to match. So if you start with log base 3, they're all going to be log base 3. Okay, so that one's very similar to the one before it. Now we can also put these together. Let's say we have natural log of 4x over y. Natural log of 4x over y. And you say, okay, well, I have division, and I know that division breaks up as subtraction, but I also have multiplication right here, and that breaks up as addition. So anything in the numerator is going to break up as addition. Anything in the denominator is going to break up as subtraction. So we're going to get natural log of 4 plus natural log of x minus natural log of y. Okay, so natural log of 4 plus natural log of x minus natural log of y. Oops. So anything in the denominator is going to be a minus. Okay, so that's what it looks like putting them all together. Okay, and the last of our properties here that kind of tie in all these exponential rules is this one. Log base a of m to the r is equal to r log base a of m. So this rule says that an exponent inside the logarithm is the same as a coefficient outside the logarithm. And this one is probably one of the weirder ones to look at. So let's look at why this works. Okay, so let's say we have log base a of m to the r. Well, what does an exponent mean? It means you're going to multiply that thing that many times, right? So this is log base a of m times m times m, and we're going to have r of them. Okay, so we do that r times. Okay, so like if this was m to the 9th, we'd have 9 m's here. All right, and then our multiplication rule says that we can break this up as addition. So we have log base a of m plus log base a of m plus log base a of m r times. Okay, so now what do we have? We've got r of these things. That's just basic addition rules. We've got r log base a of m. Okay, so this one comes from a combination of the definition of an exponent and multiplication combined with this product of sum rule that we saw before. Okay, so what this one means is if we have log base a of x to the 3rd, that's the same as 3 log base a of x. We can bring this exponent, bring the exponent down to the front. All right, and if we have log base 2 of x plus 1 squared, okay, the one thing that we need to check, does that exponent go to the whole thing? Yes, it does. So we can bring that down to the front. We've got 2 log base 2 of x plus 1. Okay, and let's say we have log base 5 of x squared plus 3. All right, can we bring this exponent down? We cannot, because it doesn't go to the whole thing. The exponent has to go to the whole logarithm, and this one does not, so we cannot simplify this one. So we're just going to leave that one alone, okay?